All right, so in this video, and really in this section, I'm going to start talking about equivalent resistances, basically combining resistors to make an equivalent resistance that basically serves the same function and functions the exact same way in the circuit, but allows us to simplify the math and the algebra for solving these circuits. But first, I need to talk about what it even means for two elements of a circuit to be in series, okay? So let me grab my highlighter here. Two elements are in series if, and there are two conditions here. The first condition is that they share one single node, okay? And so if I have two elements connected, let's say I have a voltage source and a resistor connected like this, these two elements, so the battery is connected to, or the voltage source is connected to this node, and it's also connected to this node. While the resistor is connected to this node again, this pink node, and it's got its own second node in green. So we can see that the voltage source and the battery, they share this, or sorry, the voltage source and the resistor, they share this one single node. So this is a candidate for a series circuit, or two series elements. The second condition to make sure that two elements are in series is a very important one because a lot of people mess this one up. The same current flows through them. So both elements have to have the same current, okay? And so let's take a look at this combination here. So if I'm looking at this combination of components, I have my voltage source and I have my resistor. They're connected to this pink node that I'll put a little dot here. And let's just recall what we talked about with KCL. The sum of the currents into this node have to equal the sum of the currents out of the node, the sum of the currents out of the node. Well, if the current coming in is the current through the voltage source, and the current coming out is the current through the resistor, and there's nowhere else for current to flow in this circuit, then clearly these two elements are they do have the same current flowing through them. They do share one node, so these two elements would be considered to be in series, okay? However, I could add another path here, and maybe I could add another resistor here, okay? Now, if I do that, I have to reassess because it might look at first like these two elements are in series because they were just in series. Why would me adding a resistor here mean they're no longer in series? Well, the reason is because of this condition right here. The same current has to flow through them. And because of KCL, if I have this current I1 coming into this node, I know that I'm going to have two currents leaving that node. I'm going to have a current I2 and a current I3. And so because there is going to be some current flowing here, I cannot say that the voltage source and this resistor have the same current flowing through them. Therefore, they are not in series, okay? So let's move on to the next. I think that this will just get clearer and clearer as we go, but let's move on to the next slide. So I want to show what it looks like if I have two resistors in series, okay? So the reason why I care particularly about resistors in series is that I can make my circuits a lot simpler if I combine resistors in series. What does that mean? So if I'm looking at a resistor and then I connect another resistor here and one more resistor here, and then I draw maybe a voltage source, and then I ground my circuit. Let me get my highlighter. All three of these resistors are in series because let's say R1, R2, and R3. So R1 and R2, they definitely share one node. They share this node, and they don't share any other nodes. And they will certainly have the same current flowing through them because, again, the current into this node has to equal the current out of that node, and there's nowhere else for current to flow. So R1 and R2 are for sure in series. Now let's look at R2 and R3. R2 and R3 they share a single node. They both share this node. And again, the current into that node has to equal the current out of that node, so the same current flows through them. So ultimately, these three resistors are in series. and therefore they can be combined. Well, what do I mean by combining them? Let's say that this resistor was 1K, this one was 2K, and this one was 3K, right? Well, I can equivalently draw this circuit by simply adding R1 plus R2 plus R3, and that gives me an equivalent resistance of 6K, right? 1K plus 2K plus 3K. And so I can draw this circuit just like this. And now what I can do is, let's say that this was a 9-volt source, 9-volt battery. And let's say that I was interested in determining what's the current flowing in my circuit. Well, if I wanted to do it on the left-hand side, I'd have to do a KVL loop, right? So I can go plus, minus, plus, minus, plus, minus. And I would write, I'm going up across my 9-volt battery, so I'd write 9 volts minus I times 1K minus I times 2K minus I times 3K equals 0. That's my KVL. Now I can group the like terms, and I can write that 9 volts minus I times 6K equals 0. 9 volts equals I times 6K, and therefore I is equal to 1.5 milliamps. Okay? And you can even see the equivalent resistance pops right out of the algebra when I combine like terms. That's the proof that I can combine like resistors in series. But to skip this KVL step is really nice, because now I have this really simple circuit where I know that the voltage here is 0 volts because this entire node is at ground potential, right? And then this node is at 9 volts. So I can take my very simple Ohm's law, which says V equals I times R, and I can say 9 volts minus 0, which is my drop across my resistor, is equal to I times 6K. 9 volts over 6K gives me my I, which again is just going to be 1.5 milliamps. Okay, so the key takeaway here is that anytime I have two resistors in series, I can just add them, or 3 resistors, or 4 resistors, or n number of resistors. The equivalent resistance of n resistors in series is just the sum of all of the resistors. This is the very fancy mathematical way to write that. I don't even know if it's necessary to write it that way. All you need to know is, here, let me just write it out real simply. Actually, I shouldn't get rid of that. Let me just say that in general, let's write it up here. In general, R equivalent for n resistors is equal to R1 plus R2 plus Rn. Okay? Hopefully that's clear. It's very simple. If you see resistors in series, you're welcome to add them, and you can go ahead and work the problem out that way so that you can very simply solve for the current. And then if you wanted to go back and solve for these voltages, now you know the current that's flowing. We just determined it's 1.5 milliamps in both of these cases. So you would know that this is 1.5 milliamps, and now you can go ahead starting with 0 volts here, and you can go and solve for this using Ohm's law, and then solve for this using Ohm's law, blah, blah, blah. Of course, we know how to do that now. So without making this video any longer, I'm going to go ahead and stop, and then I'm going to solve another example problem using resistors in series and showing how to combine them. And we're going to sort of unlock another tool in the next video called the voltage divider.